Last time we talked about the technique of implicit differentiation. So today we're going to use that technique to help us find derivative formulas for inverse functions. So you've likely heard of inverses before. It's useful to think of things in this way. Let's say that this is you at home. You at home would like to be downtown you. What you will do is take some sort of transportation to get there, whether it's walking or taking a bus or a cab or an Uber or something. And so there's some sort of function that takes X and turns it into Y. It has to be a function. It can't turn you into two different people. Now, at the same time, when you are there and you're downtown and you're satisfied and it's time to go home, you've got to get back. So if you are taking a SkyTrain, let's say the Expo line westbound, but if you want to go back, you still take the Expo line, but it has to be going in the other direction, eastbound. And so in that sense, there is a related function that takes you back to where you were. So we call it F inverse, and the -1 means inverse, not power. And so there's a relationship between the two. In the first case, X is the input and it becomes an output of Y. And so you start at X and you end at Y. But in the second case, you start with Y and you end at X. And then that means either one of these statements is just two different ways of relating the same values X and Y. And so what I like to call it is the switcheroo. So if you started with Y is isolated, and let's say for some reason you want to get the X by itself, you can just switcheroo and put the inverse function onto the other side. And you've still got the same X and Y connected, they just have a different input and output. And that's essentially the basic idea behind a function and its inverse. But there's a really important condition that a function has to have to be invertible. A function has to be what we call 1-to-1. Basically, it's telling you the following. If it takes two different inputs and takes them to the same location in the output, so if the function f can map two different numbers to the same output y, there's a problem going back. When you try to undo that and map y back to the original, the inverse is no longer a function. So we can't do this. Being 1-to-1 means that any output comes from only one input. And the easiest way to check whether or not a function is 1-to-1 is the horizontal line test. So the vertical line test tells you if something is a function or not, but the horizontal line test tells you if it's an invertible function. So what we are going to do is tackle some of the more common inverse functions in this way. We want to find the derivatives of these very common inverses. Logarithms and inverse trig functions. And you might say, well, logarithms, why are logarithms inverses? Remember that logarithms are inverses of exponential functions. Here's the question. If I tell you that y is the natural log of x, what's y prime? We are going to use the switcheroo to write this in terms of an inverse function and then use implicit differentiation. You may or may not remember, but the graph of a logarithm looks like this, and it passes the horizontal line test. And that means it has an inverse. Here's the idea. We will start with our given relationship. Now, I don't know what y prime is. I would love to find it, but I don't know a differentiation rule. And so here we now do the switcheroo. We are going to get the x by itself. So that means we're going to take this logarithm and put it to the other side, but to do that, it will turn into its inverse. So another way of thinking of it is we have to exponentiate both sides. And now we can find y prime. We are going to take the derivative of both sides because I know something about the derivative of the exponential. And this is the whole implicit differentiation process we did last time. So if I were to take the derivative of both sides, this is easily found to be 1. And this is the implicit differentiation idea, and we need to use the chain rule again. The derivative of e to the something is going to be e to the something times the derivative of that something. the derivative of that something is just what we are calling y prime. And so we've got y prime times e to the y is 1, and we've successfully found a formula for y prime. Now, unlike what we were doing yesterday, it's actually possible to put things back in terms of the original letter x. E to the y is x. So we'll get that y prime is 1 over x. So the derivative of natural log of x is 1 over x. And note that the domain here is that x has to be a positive number. At the same time, we can do this if we are trying to figure out the derivative of any logarithm base. If we would like to figure out the derivative of this, we'll have to do the switcheroo again. We are going to use the inverse. We are going to move the logarithm function over to the other side. Once again, this logarithm has the same picture as above. It's 1 to 1. And so when we move log base a to the other side, it becomes a to the y. This is much better because I know the derivative of a to the y. So if I were to take the x derivative of both sides, I get to use this idea of implicit differentiation again. I know the derivative of x with respect to x is 1, and I know the derivative of a to the something is a to the something natural log of a times the derivative of the something. And that's what the chain rule tells me. This is just what we are calling y prime, and a to the y natural log of a just hangs out there from before. So we'll get 1 over a to the y times natural log of a. But just like in the last case, I know what a to the y is. And so I'll end up getting 1 over x times the natural log of a. So I get my next shortcut. The derivative of log base a to the x is 1 over x times the natural log of a. Now that we have developed these shortcut formulas, we can just use them. For example, the derivative of log base 10 x over x minus 1, I can certainly do this. I just have to use the chain rule. This would be our inner function. We can call it u, and our outer function would now be log base 10 of u. And so the chain rule would tell me, okay, take the derivative of log base 10 of something. So according to the result that we just got above, this would be 1 over u times the natural log of 10 times the derivative of whatever u is. And so now I would go ahead and resubstitute for u. So I'll get x over x minus 1 times the natural log of 10 times the derivative, x over x minus 1. This expression, I'll need to use the quotient rule on. This is a multi-level fraction, so I can bring that layer up. And so I'll get an x minus 1 over x times the natural log of 10. Quotient rule says the derivative of the top times the bottom function, subtract the top times the derivative of the bottom, all over the bottom function squared. All of those derivatives are relatively straightforward. So I'll get an x minus 1 minus an x over an x minus 1 squared. These x's will cancel. This x minus 1 can cancel with one of those. So at the end of the day, I'm left with negative 1 over x times x minus 1 times the natural log of 10. So all we are doing is adding another shortcut formula to our repertoire. Now there's a bit of a note here that I want to make. The shortcut formula for the natural log is given by this, and in this case the domain is x greater than 0. Now for some reason you may want to take the derivative of the natural log of negative x where x is on a negative domain. If that's the case, then you could use the chain rule, and the chain rule would say, okay, the derivative of the natural log of something would be 1 over the something times the derivative of that something. You'd end up with a negative 1 over negative x, which is 1 over x. But this time it would be defined for negative values of x. We have now shown that the derivative of the natural log of negative x is also 1 over x. But this time it applies only for negatives. And then mathematicians in their infinite wisdom decide to confuse students. So they'll say, ooh, look, we can combine both formulas. And they'll say, this is so much better. Because we could either use a positive x or a negative x inside here, why don't we just write it as the natural log of the absolute value of x? And at the end of the day, our formula will be the same, a 1 over x. Unfortunately, this causes students a lot of confusion. Don't stress yourself out about this absolute value.